And the next speaker is Jan-Erik Beck, and I can't see with my eyeglasses, from the Max-Planck-Institut of Radioastronomie in Bonn, Germany.
Right, okay.
The floor is yours, and you have 40 minutes.
Thank you. So, first of all, thank the organizers, the Academy and also the Crafoord Foundation for the invitation. It's a pleasure for me to give this talk. And I'm active in this field since almost 50 years. And I almost went to solar physics for my PhD, but I did not get an interesting PhD topic in Germany. And at that time, when I started my PhD, the new 100-meter telescope in Effelsberg was just in place, and that was so amazing. I thought I have to go there, and that's why I left from very near to very far away, and now I can talk to you about magnetic fields in nearby galaxies. And a lot of that is indeed connected to Gene Parker. So I met Gene only once on a conference I organized with a few colleagues in Heidelberg in '89, and he gave the introductory talk about the sun, of course. And I hoped to meet him here again, but sadly that did not work out. I even brought a book from him to get a signature. Too late, so that's a really very pity. So Corona prevented that. So, in solar physics, everybody agrees that magnetic fields are not only existing, they are crucial. In my community of galaxies, this is not the case. So many people believe magnetic fields are unimportant, and if they are there, okay, they play only a small role. Although they are really everywhere, because the interstellar gas is ionized, they are very easy to generate. There are no monopoles, so that they are very hard to destroy. But the problem is they are very difficult to observe. In my community, there is now increasing evidence that magnetic fields may be important. And there's a recent simulation showing that galaxies, even in stars, look different if you have magnetic fields allowing to affect the evolution of galaxies. So this is a simulation. Their optical disks look different and they are larger. So there is some hope that even in my community, people now getting more and more interested in understanding magnetic fields. And indeed, there are a lot of fundamental questions still to be answered. When were the first magnetic fields generated? Did they exist before galaxies formed? How fast were they amplified, and how did they affect the evolution of galaxies? And there are many tools to study magnetic fields, and I will talk about the first three ones: magnetically aligned dust grains, which can be observed in polarized optical infrared submillimeter or millimeter synchrotron emission, and Faraday rotation. There are more effects, Zeeman effects, Goldreich-Kilafis, and the velocity gradient I will not have time to talk about today. But before I come to results, I have to bore you with a few definitions, because definitions are important so that we can speak the same language. And I have to admit that the language, even in our community, is not always the same. So I will tell you what my language is, or what my dialect is. So we all agree that there is a total magnetic field, which is everything together. And we split that into a random, isotropic random field, an anisotropic random field, and a regular field. And this distinction between isotropic and anisotropic random field, that is really very important, because it can be distinguished observationally. And these two together, they are added as a so-called ordered field, because it looks ordered. An anisotropic turbulent field looks like an ordered field, but is not. Physically, they are different, but I will show you an example for that. So random fields with isotropic directions are the random ones, and the anisotropic ones are these ones here. Then there is a regular field, which the dynamo people speak about as a mean field, which is generated by a large-scale dynamo. And the ordered field is something we see in polarization, which can be either anisotropic or regular. And so just to make this clear again, so there are two types of random fields, the isotropic and the anisotropic ones here. This is from a nice picture drawing by Andrew Fletcher here. So that is something which can also be called tangled field here. That gives no polarization and no Faraday rotation. And these ones here gives polarization, but no Faraday rotation. What Faraday rotation is, I will speak about in a second. So random field can be physically turbulent. That means it has a Kolmogorov type power spectrum, has very small scales. But in observations, we cannot distinguish that from the tangled field. The tangled fields can be much large, can have much larger scales. They're produced by from regular field by tangling of gas motions, for instance, turbulent motions. And the scale can be much larger here. Okay, and the two types of the ordered field, again, to make this very clear, this is a dynamo type regular field, which gives also Faraday rotation and polarization, and that also gives polarization, but no Faraday rotation. This is the anisotropic random field. So this is just to confuse you completely about the terminology. If you look into papers of our community, you will find many other definitions, and unfortunately, there is no IRU convention yet which one should be used in future. Okay, so coming to the origins. So the regular fields, this is what the dynamo does, and here, of course, Parker's work is crucial here. Gene Parker was the first to really explain that there could be a large-scale dynamo operating in the Milky Way and could explain the fields which have been observed at that time. Random fields are just turbulent fields or tangled fields by turbulent gas motions, and then there is a turbulent dynamo. There are turbulent fields also generated by the small-scale dynamo, and in this topic here, the chairman of this morning, Axel Brandenburg, has done very significant work, and I have learned a lot about that. So just to at least give you some mathematics, this is the classical dynamo equation. This is your original equation. To have any solutions, you have to subsumize microphysics into two terms here, which is the alpha tensor, turbulence tensor, and the diffusivity tensor eta here. If you do that, you separate the large scales from the small scale motions also in B, that you get analytical solutions. And if you assume then a thin rotating disk, then many people, Gene Parker, for instance, and also other people, showed that their symmetric quadrupolar fields are generated here. But in a thin rotating disk, the azimuthal field is the strongest. The other field components, radial and vertical ones, are much smaller, so that the field is spiral. So a spiral field is something which comes automatically out of the large-scale dynamo. We know that that galaxies have spiral arms, so then the suspicion is that the formation of spiral arms in galaxies and the formation of spiral fields by the dynamo may be somehow connected, but this has not been proven yet. And I had a lot of correspondence with Gene Parker after I met him first, and one of the letters I still have. So if there's an archive of original letters of Gene Parker, I can contribute a few of them. I had a lot of interesting discussion with him, and he was telling me that in the dynamo there is no change in the sign of the azimuthal field, which was heavily discussed at that time. It could be that in the different spiral arms the magnetic field reverses its sign, and Gene said, no, this is most probably not the case. I have more of these nice letters here. That was very interesting, and he responded immediately in all handwritten and was sent by normal mail. And this is something that took at least a month to arrive at my home place here. Okay, so what can we learn? That's what all definitions. So what can we learn about magnetic fields? So the simplest thing is you observe a galaxy with total radio emission. That's what every radio telescope can easily do. And total radio emission, mostly synchrotron emission, is a tracer of total magnetic fields. So this is a typical image of a typical spiral galaxy, and you see 6946. You see there are some sort of spiral arms here, and the synchrotron emission is directly related to the total magnetic field strength. With some small problem, there is this electron density, this cosmic ray electron density. You have to know something about that, and you can determine that one. Unfortunately, we don't know much about the electron density. Alan Zweibel in the next talk will say how that can be done, for instance, with help of gamma rays. Normally, we don't have that, so we have to do an assumption here. Okay, if you want to have more of these nice images from galaxies, look into the atlas we have produced in our institute. There's an atlas of bright, nice magnetic fields in galaxies. I don't have time to show all of them. So coming back to the magnetic field, so if you have, if you want to get the electron, the magnetic field strength, you have to assume that there's equipartition between the total cosmic rays and the total magnetic fields. In that case, you can really determine the magnetic field strength. Is equipartition valid? There's a lot of discussion about that. Alan Zweibel also has worked on this one, and it seems that on large scale it's fine. So the field strengths are okay, but on small scales you may be wrong by a factor of several. So if you apply this so-called equipartition, then the field strengths are of that order here, between 10 and 15 on average. In spiral arms it can be larger, and in starburst galaxies can be up to 100 microgauss. So we use still microgauss. If you prefer Tesla or nanotesla, you can easily transfer these numbers here. What does it mean? Are these fields dynamically important? And for that you have to compare the different energy densities. The energy densities of magnetic field, of the kinetic turbulent energy, and of the thermal energy. And the thermal over magnetic gives a plasma beta, and that tells you something about the dynamical importance. So we have done that for several galaxies. This is one example, IC342, doesn't matter. You may not know that one. This is the energy density as a function of radius, and you see that the turbulent energy density and the magnetic energy density are similar. So they are of the same order, whereas the thermal energy density is much lower. So the interstellar medium seems to be a low beta plasma. That means magnetic fields are dynamically important in galaxies. But this is also interesting. That tells us that the turbulence and magnetic fields are somehow related. And this is a puzzle, because models at the moment, they cannot explain that. So this is one set of models by Federat et al. And what they find is that the ratio between the magnetic and the kinetic energy is only up to 10% for different Prandtl or Reynolds numbers here. They cannot go higher than 10%. And the reason is probably quite simple, that the simulations, they work in the range magnetic Prandtl number up to 10 and the kinematic Reynolds number up to 1,000, and that is not realistic. So the real Prandtl numbers are much higher, also the Reynolds number much higher in the interstellar medium. That means the present simulations do not have the resolution really to show the full amplification of magnetic fields here. So that is still not realistic. Maybe in addition we have additional amplification by compression and shear. That is another possibility. Another proof that in principle turbulence and magnetic field are connected, and magnetic fields may be generated by turbulence. This is the radio far-infrared correlation, and this is one of the latest pictures here. These are more than 15,000 galaxies. This is the luminosity in radio against the luminosity in far-infrared. This is an amazingly close correlation. I think it's one of the closest correlation existing in the astrophysics at all, with a slightly non-linear slope here. And that is something which can be easily explained if you transfer the radio emission into magnetic field strength. And if you transfer the far-infrared luminosity into a star formation rate, then you get a similar relation with a different exponent, and the exponent has been measured of the order of 0.3, and this is well in agreement with the models of small-scale dynamo. So the slope is indeed what you would expect from a small-scale dynamo. And Axel has worked a lot on this dynamo here. So that seems to work fine. So for the total fields, life is obviously a bit easier than it has been before. Magnetic fields are dynamically important. The magnetic field is related to the star formation rate, and the field amplification can be explained by the small-scale dynamo. But the resolution of the MHD models has to be increased. They are still not realistic. Okay, so the more interesting point is if we now go to the ordered fields. Ordered fields can be seen by polarization. And polarization now is also produced, results are produced by this nice telescope here, and there's a polarimeter called HAWK on board of the SOFIA telescope, and in the recent years there have been a lot of new results from the far infrared side here. The far infrared is very powerful to measure magnetic fields, as you can see on this picture here, but it cannot show the field directions. It just shows you the orientations of the field. And it cannot give you ideas about the total field strength. On the other hand, it shows you the ordered fields in the cold gas, whereas the radio emission shows you the magnetic fields in the diffuse ionized gas. So combination of the far infrared polarization with radio polarization gives you some idea of what the different components do and whether these are the same or they are in different phases of the interstellar. They can be different here. Just give you one example here, recent paper of a barred galaxy here, and this is a combination of the data from the far infrared polarization and the radio polarization, and this is another indication that there is an inflow. So in this case it's not a wind but an inflow of matter, and this inflow transports angular momentum outwards and allows inflow of matter of about solar mass per year, and that could be the reason why the AGN in the center of this galaxy is fat. So Lorentz forces are very nice to explain why AGNs exist at all, and you don't need any gravitational instabilities. It can be all by magnetic fields. But the polarization angles are different. In the infrared, these are the blue ones here, and in the radio, these are the red and the yellow ones. They are different because here the material is compressed at the edge of the bar, and on the other side, and in the radio you see a spiral field, which is probably the reason, the origin of a large-scale dynamo here. Now coming to one of the most famous galaxies at all is M51, the spiral galaxy, and there we have excellent data, but we have learned something really new. We see not only polarization in the spiral arms, we see also polarization in the interarm regions. That's nominated B here. A is in spiral arms here, and B is in the interarm region. So the idea is that what we see here as B is maybe a large-scale field from a regular field from a large-scale dynamo, and what we see here is probably anisotropic turbulent field, and the proof for that is also given in a recent paper. If you plot the total and the polarized emission against the star formation rate, this is again the another representation of the radio-infrared correlation with a slope of slightly more than 1. But the interesting point is that also the polarized emission, that means the ordered fields, also get stronger with increasing star formation rate. And star formation rate is varying on scales of millions of years, and the large-scale dynamo cannot react on that. So what we see here must be an anisotropic random field, so a field which has been produced by a large-scale dynamo, but then has been sheared or compressed by the local effects in the spiral arm. So this is a first really almost proof that anisotropic random fields are very important in spiral arms here. So again, comparing the radio with the infrared, amazingly the pitch angles of the spiral arms is a function of radius in the radio and in the infrared. Infrared is the blue one, and green and yellow is the radio. They agree very well. So that is amazing that the magnetic field in the cold gas and in the diffuse gas, they are mostly the same. Only in the outer parts of the galaxy where the interaction with the companion plays a role, then the two start to deviate. So one could say, okay, why do we need SOFIA HAWK if we can do everything from ground? But if you look in details, there are significant differences. We can learn how the magnetic field in the cold and in the warm gas are connected. So the next part, and then now it's getting really interesting, is Faraday rotation. This is something we can only do in the radio range, not in any other in other ranges. This is a tracer of regular fields. So regular fields, they can only be produced by a large-scale dynamo. There is no other theory at the moment explaining large-scale regular fields. To be very clear, that is not possible. Not by shear, not by compression. That needs the large-scale dynamo here. So Faraday rotation means that the polarization angle is rotated according to the field along the line of sight and the thermal electron density, and all that is called the rotation measure. So in the past, people did fits of the polarization angle against lambda square. Now we have more modern techniques, but I have no time to go into that. The same problem as before. If you want to measure the regular field strength from the rotation angle, you need assumption about the thermal electron density, but there is quite good assumptions that the thermal energy density is related simply to the star formation rate. So that seems to work quite fine. And now I show you my favorite galaxy, which saved my PhD. After I observed the wrong galaxy, then I moved to this one and said, oh wow, what is that? It's a simple Andromeda nebula, but look what's going on in the radio range. It's a very nice ring here. It's a ring of 20 kiloparsec. It's not radius, it is 10 kiloparsecs, 20 kiloparsecs diameter. It's amazing. This was so amazing that we wrote many papers and observed it again with my beloved telescope, which just became 50 years old. And last year we made and the degree of polarization is up to 50%. We couldn't believe that. How is it possible that the magnetic field is so ordered in a normal galaxy? That was. I also, as somebody said, you don't believe your own observations until somebody else confirms them, and indeed this high degree of polarization is correct here. And then we did the Faraday rotation, and the Faraday rotation was proving that indeed it's not only a ring, it's a coherent ring. So Faraday rotation is negative here and positive there if you subtract the galactic foreground. So it has, if you go along azimuth here, it has a sine wave variation, and that is exactly what the dynamo predicts. And last year we made a more careful analysis, and we found not only one wave, we found two waves. We found a second wave superimposed on that. We found two, what the dynamo calls dynamo modes, azimuthal dynamo modes, m equal to 0 and 1. So this is a prototype of a large-scale dynamo in galaxies. So it's only one galaxy is almost as nice, but these are the only really nice cases here. 6946, it has a dynamo operating in the interarms here. One arm here, one arm there. And if you look at the Faraday rotation, you see that here the field is going inside, and also on the other side it's also going inside. So how can that be? The field lines must close. They close somewhere in the halo here. But we believe that these inward-directed magnetic arms, as we call them, this is a signature of the large-scale dynamo action. So I made a question mark here for those people who don't believe that is really the case. But I think it is true. So you can play around with the dynamo modes, azimuthal dynamo modes in your computer. Even I can do that, although I'm not a theorist. So you can say, this is the ground mode. This is just going around and around on one direction. This is the ground mode. The next one is a bisymmetric mode, which goes in and out. And then you can combine them. You can have a quadrisymmetric mode, or you can have a combination between these two ones here. And then you get something inside and inside. So a combination of these two gives you these magnetic arms here. So I think it's a good indication that this is another large-scale dynamo. Okay, but there are also bad cases. So there's, again, M51. What's going on there? This is a Faraday rotation. There's no pattern seen there. Why? This nice M51 does not have a large-scale dynamo. It is there if you look very carefully, but it's extremely weak. Why does this galaxy not have a well-pronounced dynamo? We have no ideas. It may be related to these pads or these spots here, which show that maybe they are large-scale fields, and maybe there's some outflow. Maybe the wind is what's going on there, or what Gene Parker calls instabilities here. This is an original sketch, handmade by Eugene, one of the letters he sent to me, which was later then became, it was already published in '66. I don't know why he plotted that again, maybe just to please me. He showed me, give me this picture. This is the Rayleigh-Taylor instability, which shows that the magnetic field has also vertical fluctuations, which are not modeled by the dynamo, which come in addition. And these Parker instabilities, we have really found several of them in several galaxies. So one of them is the again M31, where we have observed one region with higher resolution, and you see these fluctuations of Rm in this galaxy. If you go into very high resolution, we don't have rotation measures, we see only the polarization vectors, but you see these wiggles here. This is the best resolution we have of any external galaxy, of about 100 parsec here. So that is also an indication of Parker loops, and the best ones have is for this galaxy M74, where the Faraday rotation here, if you go along this arm, shows this periodic variation here. So this is quite clearly evidence of Parker loops. Okay, so closing this part of my talk, we have seen, according to the dynamo theory, we have seen several modes, m equal to 0, 1, and 2, for a couple of galaxies. And always, except for one case, the ground mode is the dominant one. So that seems to agree very well with dynamo theory. And another thing agrees with dynamo theory. All these galaxy patterns, these spiral patterns, all these patterns are spiral, so they have a radial component. If you now look whether the radial component is pointing inwards or outwards, you find the same occurrence for the inward and as for the outwards direction, and that is exactly what the dynamo model says. The direction of the radial component should be arbitrary. It's not a preferred one. It does not depend on the sense of rotation. It depends on the initial conditions here. Also, that is very well in agreement with dynamo models. Okay, so. A very important thing for dynamo modeling is if you compare the relative strength of the magnetic fields here. So if we now split the different components into isotropic, anisotropic, and regular field, the one important number is the ratio of the regular over the isotropic random field. Dynamo theory says that this should be of the order of 1. But it is not, and that puzzles my dynamo colleagues very much why this ratio is so low here. So there's something which does not allow the regular field to reach the level of turbulence here. And the other surprise is that the ratio of between anisotropic and total random field is quite high. So the anisotropy, everything which shears and compresses magnetic fields, seems to be very important in galaxies. So that is also something which is a surprise and needs to be explained. So just briefly coming to existing simulations, numerical MHD models here. So what do they have to do? They have to explain, no, they don't explain, they assume a seeding of magnetic field. Then they have to explain field amplification by the small scale dynamo, field ordering by the large scale dynamo, then in addition tangling and compression. So if you do it in boxes, then everything is fine. There's a nice paper by Fred Gent on a small box here showing that there is a superposition of regular field with turbulent field, and that is something which also it seems that we observe. But we need global models, and there at the moment the MHD models they fail. This is one set of models by Rüdiger Packmo et al. And you see this is a different field directions. There are no strong magnetic arms here, and this is, let me just see, this is the radial component here, this is the azimuthal component, and this one is the vertical component here. This is not like at least some of the galaxies look like. And the reason is that with their resolution, they cannot model the large-scale dynamo. The large-scale dynamo is not yet included. A different set of models by Leo et al. Looks a bit more promising here. So you see some traces of magnetic arms here, but also that is not yet how the galaxies look like. they also don't have the large-scale dynamo. And the third group of people from Garching or Munich, they claim that they include large-scale dynamo and shear and also cosmic rays, but their magnetic field look very different from what we see. They don't have magnetic arms; they have huge halos of magnetic halos, and the field looks dipolar. This is something we do not observe. So, summary of this ordered field part is that they are spiral. They have large-scale patterns in the Faraday rotation. We still do not know whether they are higher modes than the third mode existing in galaxies, and we need clearly we need higher resolution, and that is something which the forthcoming telescopes can hopefully do. Request to theory is we need combined MHD models, including large-scale and small-scale dynamo. We have to learn about the spectrum and strength of dynamo modes. We have to understand how tangling works, and we have to understand the origin of anisotropy in galaxies. Okay, but now coming to a third topic which is related to Parker's work. I have already talked about large-scale dynamo and the Parker instability, but what about the winds? So do we see evidence for galactic winds? And so I will now talk about galaxy halos. That means galaxies, they are observed edge-on, so where the halos can be seen. And I just want to mention an important problem related to the halos of galaxies. As mentioned already before by some of the speakers, helicity is something which is conserved. But the large-scale dynamo produces large-scale helicity in the disk of a galaxy. And if helicity is conserved, then that may suppress the dynamo. And that is something Axel Brandenburg, chairman of This Morning, pointed out already in 2005. So how can we overcome that? The dynamo obviously exists in nature, but theory says it cannot exist because helicity is conserved. Okay, so we have to get rid of the helicity by ejection. And one possibility is that the small-scale helicity is ejected by outflows. But if you look in detail, Luc Chamandi has done that. If the outflows are too strong, then the dynamo is suppressed again. So if the outflows are too weak, you don't have dynamo action. If it's too strong, you also don't have dynamo action. So you must have some intermediate range of outflow velocities to let the dynamo operate in a galaxy. So do we have evidence for winds? Yes, we have. This is NUC 253 combined from different from this atomic hydrogen, soft X-rays, and H-alpha, and also magnetic field vectors. So you see there is a lot of indication that there is magnetic field going out of the galaxy. And Volker Hesen has measured the outflow velocity by modeling the radio profiles and found that the outflow velocity is related to the star formation rate. So the higher the star formation rate, the stronger the outflow velocity. And we also know, I have shown you before, the magnetic field is related to the star formation rate, so maybe the outflow velocity is related to the magnetic field strength. It's a possibility. So is the wind driven by magnetic fields or by star formation or both? We don't know that. So are there indications that indeed there is helicity in these outflows? Yes, there are. There is one observation of this pattern again in the halo of a galaxy, where from the rotation measure we see indication of a helical field, which just means the rotation measure is just flipping from one side to the other side here. There's only one region here of this galaxy, but at least there is some evidence that helical fields exist in galaxies. And the most amazing result is this one. This is a galaxy with one of the largest halos we have at all, 4631. And again, we have this output pattern of magnetic field orientations here. And the color is a rotation measure. And you see there is a periodic variation of Faraday rotation, which is plotted here. We call that giant magnetic ropes. There could be helical ropes, and they could be related to the huge sort of Parker loops, but it could also be related to this outflow of helical magnetic fields. And that is what Glenys Farrar plotted, how it could look like, but unfortunately there's no dynamo model existing yet producing such a nice helical. No, there is one. There is one by one model is existing, could explain this helical field in the halo. The name comes back to me in a second. Okay, so halo fields, they don't have simple quadrupolar or dipolar patterns. They are X-shaped, so that is different from the classical dynamo models. And as we have learned, classical dynamo models don't work anyway because they cannot conserve helicity. We need something in addition. Fields are symmetric. They extend to many kiloparsecs from the plane, and they have helical indications for helical patterns, but we need dynamo models including outflows, and that is clearly what needs to be done. And then at the end, I just add a few remarks on the Milky Way. I've promised you to tell you what about the Milky Way. The Milky Way has a big problem. We are sitting well inside. So if we produce a map of Faraday rotation, which gives us the large-scale pattern of the magnetic field, we do not know where this Faraday rotation is coming from. These are background sources, more than 55 sources in the background shining through the galaxy. And here are negative Faraday rotation. Here are positive Faraday rotation in the inner parts. It seems to flip between plus and minus here. So the traditional explanation is that the local field and the local arm where we are sitting with our solar system, that is from here going around to here, this is a symmetric quadrupolar field as in other galaxies. But what about the inner part here? That seems to be antisymmetric, a dipolar field. But recently, Rüdiger Packmo has shown that this may be completely local. So that is a by chance effect of local magnetic fields. We should not take this too serious. It may not indicate a dipolar halo field, as some people have claimed. But that is unclear because the distance of all these features is not known here. So another word to the helicity, and helicity is important in the Milky Way. So Axel has pointed out that in 2014, and also Kadi Orlou in Göteborg has pointed out that helicity can be measured in galaxies by comparing polarized fraction with Faraday rotation. So the combination of these two data sets can in principle do that, but it's very hard. In external galaxies that has not been done yet. In the Milky Way it has been done recently by Jennifer West, and indeed there seems to be left-handed helicity in the northern hemisphere and right-handed helicity in the southern hemisphere. So there is indication for helicity also in our Milky Way. So what about the large-scale structure of the magnetic field in the Milky Way? There is one reversal. So the local Orion arm, here we are here, this galactic center, has a clockwise magnetic field, and the Sagittarius inner arm has an anti-clockwise. So there seems to be a reversal of the large-scale magnetic field. These reversals have been seen only in one external galaxies, but dynamo theory allows them, although Gene Parker told me in 82 that should not be, no, 92, not exist. It is possible and also in dynamo theory that there is a reversal. Whether there are more reversals here towards the outer galaxy or the inner galaxy, we just don't know. We don't know the large-scale field. So we know much less about the magnetic field in our Milky Way than we know for external galaxies. And hopefully things will become better soon. We have an ultimate radio telescope, which is just under construction since this year, the Square Kilometer Array. Now that is a telescope in the high frequency range, will be built in South Africa. That will allow us to do all these measurements with at least one order of magnitude improved sensitivity and resolution. There's also low frequency part that will be built in Australia, but that for our purpose is of less interest. So that is something I can talk more to you about if you want to learn more about that. It's coming too late for me, but for the younger people here, this is a telescope to go for. Okay, thank you.